All right, let's talk about 3.3 here real quick. So the power function. So a power function for your k and p in the real numbers is given by the function f of x equals kx to the p. So what we're looking at is k is some real number, and so is p. K is the coefficient, and p is the power. So in this example, we said, consider these functions. So f1, f2, f3, so on and so forth. Those are just function names. I didn't want to call them f, g, h, j, so on and so forth. And I said all of these different functions. I said, which of these are power functions? So 5x, x squared, 5x, x squared, x cubed, 1 over x squared, square root of x, cube root of x, and 2 to the x. Which, I said, if any of them are power functions. Well, let's look. You'll notice that all of them, except for f sub 9, are power functions. How do you know that? Let's look through this real quick. You can write 5, that is 5, as 5x to the 0. It's the same thing. And that looks like a number times x to another number. Just x from up here can be written like this, 1x to the first, 1x to the first. That is, it's a number times x to another number. X squared up here can look like another number times x to another number, like that. So that's a power function. That's it. X cubed is 1x cubed. That's a number times x to a number. 1 over x up here can be rewritten like this, guys. Can be rewritten like this. 1 times x to the negative first. It's exactly the same thing. Dividing by a number is the same thing as multiplying by that same number to the negative power. Well, notice that p up here can be any real number. So we're good to go. Negative 1 is certainly a real number. 1 over x squared, well, that's just this. 1 times x to the negative second. That's a power function. A square root, no problem. That's just a fractional power. That's x to the 1/2. 1/2 certainly a real number, so that's a power function too. Same thing with cube root. That's just x to the 1/3. However, 2 to the x is not a power function, because in the definition of a power function, x is raised to a number p. Here, it's a number raised to a power, and that's different. So, out of all of these functions, only 2 to the x isn't a power function. Let's move on. I said, look at the graphs of x to the n for x equals 2, 4, and 6. What patterns can you notice? Do the same for 3, 5, and 7. Look at what happens as your x values increase in both directions. And you're welcome to go on Desmos and do that. Graph x squared, x to the 4th, x to the 6th, and so on and so forth. Look at them. And then the same thing for 3, 5, and 7. But I'll give you the long and short of it here. These are your evens. These are your odds. Your even functions are going to look like this. At their ends, that is where they're going as we get infinitely big, that is as we get infinitely big in either direction, we're going to infinity in both cases for these guys, assuming they're positive. And it is. This is positive. And if we're odd, that is if it's x to the 3rd, x to the 5th, x to the 7th, or just x, we're going to look like this towards the end of these guys. That is, as x goes to negative infinity, y goes to negative infinity, and the same thing for positive infinity. So even and odd functions all look like this. It's just the higher the number, the faster they get big. But in terms of what they're doing at the end, well, that's what we're concerned with for a good portion of this. So the end behavior of a function, f of x, is its behavior as x goes to negative infinity and x goes to positive infinity. So this is x goes to negative infinity. That's how you read that. That's x goes to positive infinity. So let's tell the end behavior of f of x equals 3x to the 4th. That's easy enough. It's always going to look like what's in this red box here. So it's always going to look like as x goes to negative infinity, y is going to somewhere, and as x goes to positive infinity, y is going somewhere. We just need to know where it's going. Well, let's think about what this looks like. This is a positive even function. And you can go graph it on Desmos if you want to. But it's going to look like this. A positive even function looks like this. So I want to know, as x goes to negative infinity, Well, look at your y. Just hug the curve. Where's y going? It's going up to positive infinity. So we write that. As x goes to positive infinity, our y is, well, it's also going to positive infinity. So you'll notice as it goes to plus or minus infinity, it doesn't matter, it goes to infinity. This is shorthand if you'd rather write it that way. Up to you. But that's basically what we're doing. And the only way that I know of to show you how to do these is just to do a whole bunch of them. So let's do this next one. So this is a negative even function. Negative even functions look exactly like positive, even functions, except they're opposite. It's going to look like this. So let's think about this. As x goes to negative infinity, as x goes off towards negative infinity, our y, hug the curve, is going down to negative infinity. And you'll notice the same thing. As we go to positive infinity for the x, we're going to negative infinity to the y also. That's all we're doing. And every one of these, and I've put boxes around this for a reason, just to highlight what's going on. You don't actually have to put the boxes, and I've stopped doing that in a minute. But this part here in the box is always written. So's the y part. The part that I've written in white, that's kind of your answer. I want to know where your y's are going as your x's are going to negative or positive infinity. That's the definition of end behavior. Let's look at the next one. So here's a couple more. And I've already filled out the part that you need to fill out. So this is part of the answer for all of the answers. As x goes to negative infinity, where does y go? As x goes to positive infinity, where does y go? But what I want to know in particular is for 3,000x to the fourth. And you might be like, oh man, 3,000, that is sure is a gigantic number. Don't worry about it. It's positive and it's odd. So it's going to look like every other positive odd function around its ends, which is you're going to infinity in both directions. So write that. That's it. Here we have a positive odd function rather. So positive odd is going to look like this. Looks kind of like x cubed. And around its ends, as we go towards negative infinity, our function itself is going towards negative infinity in the y. And as we go towards positive infinity, our function itself is going towards positive infinity in the y. So that's the end behavior. All that I'm looking at is the sign of the coefficient and the parity, or whether it's even or odd, of the exponent. That's all that we do on these. Let's do another two. How about 9x to the third? I want its end behavior. It is positive and odd. So it looks like this. Positive and odd. And this time I'm only going to draw the ends of the graph. We don't know what it's doing on the inside. We have no idea what it's doing. It could be doing anything. We don't care. All we care about is the ends of it. So, as x goes to negative infinity, where's our y going? Well, to negative infinity. As our x goes to positive infinity, where's our y going? The part of the graph that we've drawn. It's going to positive infinity. Down here, this is negative, and 50,001 is an odd number. We don't even care that it's that big. It's going to look like all negative odd numbers, or all negative odd functions rather, are going to look like this at their ends. So as x goes to negative infinity, like this, where's our y going? Well, it's going off to positive infinity. It's going to negative infinity when we go the other way. That's it. That's all that you're looking at. At the very end of the graph, are you going up or down? Overall, at the very end of the graph, are you going up or down? That's end behavior. We do talk about some functions later in the future that go towards numbers instead of infinity or negative infinity. Those are called rational functions, and they're real weird. But for now, this is what we're talking about. And there are other functions that can approach numbers. Logistic functions is one I can think off the top of my head, but I digress. So you may notice that there's a pattern. All we end up caring about are just the different combinations of positive and negative and even and odd. Those that are astute among you may notice there's only 4 such combinations. So you'll notice then, in this example, it says tell the end behavior for any power function for all combinations of positive and negative k and even and odd p. So I just made this table that you should totally copy into your notes. I put k whether it was positive or negative, and p whether it was even or odd. And here's all 4 of the things. So a positive even function looks like this, and its end behavior is to the right. A negative even function, its end behavior looks like this. Positive odd looks like this. negative odd looks like this. Those are the only 4 possible end behaviors of any power function. So all you have to do is look at the k and the p. That is, look at the sign here and whether this is even or odd, and that'll tell you everything you need to know. And I think that's fantastic. So pause the video for a moment and get this copied down. It is a fantastic tool, and we're just going to use it a whole bunch more. So let's talk about a polynomial function. It says let n be some natural number or 0, like that. A polynomial function is a function of the form, and it looks like this. And you might be looking at that and saying, Mr. Bryant, that looks terrible. It's not terrible. It's just functions that, long and short of it's this, guys, end up looking something like this. So it's some coefficient times x to some other number. That is, look at this thing. What is this thing? This is a power function, right? Except this time, our n, look up here, has to be either a natural number or 0. That's all that we know about. That's the only thing. And it's just a sum of a bunch of these. These can also be minuses because these individual a sub whatevers can be negative and turn them into minuses. But I digress. That's what a polynomial looks like. You know what a polynomial looks like because you've been in an Algebra 2 class before. The example down here says, which of the functions f of x equals 5x cubed plus 3x times 2x plus 1, g of x is negative x plus 1 times x plus 2, and h of x is 5 plus square root of x are polynomial functions. I'll just give it to you. It's not that one. Why not? Because this is x to the 1/2. And you'll notice that 1/2 isn't a natural number. So that's not going to work. But these other ones can be simplified. Down here I've simplified f of x. Just actually do this multiplication and it'll look like it's supposed to. And then here, all I did, for this guy here, all that I did was just this math right here. Which you may notice is I just FOILed it out. I FOILed out x plus 1 times x plus 2 to get x squared plus 3x plus 2. And then this negative got distributed in and made everything negative. Which means that the thing in the box right here looks like, well, this up here. Which is awesome. But those are polynomials. Remember, if you've got square roots, or if you've got your rational functions like 1 over x's, or like 3 over x to the 15th, or whatever, if these are added or subtracted inside of what you're calling a polynomial function, it's not a polynomial function. Those are big no's. They have to be nice, easy-looking power functions where you can write it such that the power, the actual power, the coefficient, not the coefficient, the power up here has to be a natural number, 1, 2, 3, 4, 5, 6, 7, or 0. That's it. Now, let's talk about a couple more definitions and do a couple more examples. So the degree of a polynomial is the highest power in the polynomial. And the leading coefficient of a polynomial, it's the coefficient, that is the number out in front, of the term with the highest power. Okay? So, we're just going to do a whole bunch of these. And I've already written out degree and leading coefficient here. That's degree, that's leading coefficient. And it says, tell the degree and leading coefficient of this guy. Well, that's easy. The degree is 3, because 3 is the highest power. There's a 3, there's a 1, and there's an x to the 0 here. So there's a 3, there's a 1, and a 0. Out of those numbers, 3 is the biggest, so the degree is 3. The leading coefficient is the number that goes with that term, 2. That's it. That's the degree and leading coefficient. And if I'm going quick, it's just because there's a bunch of examples. And the more you pay attention, the more luck we have in learning this sort of stuff. So down here, let me try and trick you. Tell the degree and leading coefficient of this function. Okay, well then the degree is 2, and the leading coefficient is 5, right? I mean, up here it was the first term, right? Remember, it's the highest power. So look back down here again. Is 2 the highest power out of 2, 5, and 1? No, 5 is, obviously. So 5 is the degree, which makes positive 3, take the sign and all of that, is your leading coefficient. That's all that there is to this. That's how to find the degree. You might be like, why do we care? And it's because we're building up towards something. But first, let's look down here at this example and tell the degree and leading coefficient of the function f of x is x to the 25th minus 2x to the 387th minus x. You might be like, 25 is a big number, so that must be the degree, right? No, it's not. 387 is the degree, because that's the largest power. And then negative 2, you take the sign with it, is your leading coefficient. Because if you wrote this correctly, that is the way that we normally write it, it would be negative 2x to the 387th plus x to the 25th minus x. That way, the leading term is actually the term with the highest degree. You don't have to write it that way, but I recommend that you write it that way. So, that's all that there is to finding this sort of stuff. Let's do one that's a little bit trickier then. So we want to find the degree and the leading coefficient of this function. And you might be like, oh no. Oh no. How do we do that? It's not written in like a normal form. You got to FOIL it out first, right? Yeah, let's FOIL it out. So x, I'm going to multiply into here, and I'm going to get this step here, and then I'm going to go ahead and finish the problem. So x times x is x squared. That's how I got that. And then x times 1 is x. Still times 2x minus 2. And then let's FOIL that out. So x squared times 2x is 2x cubed. That's this part. X squared times negative 2 is minus 2x squared. Okay. We're now going to do x times 2x is plus 2x squared. And then x times minus 2 is minus 2x. Okay. You might notice that there's a minus 2x squared and a plus 2x squared, so those just cancel, and you get 2x cubed minus 2x to the first, I guess. So your degree is 3, and your leading coefficient is 2. That's it. Let me show you something else here, though. We didn't have to do all this math. We could have, instead, just multiplied together all of the x terms with the numbers in front of them. So 1x, and 2x. Watch this. 1x times 2x. That is, 1 times 1 times 2 is 2. X times x times x is x cubed. That is the leading term. That's all that we need to figure out this information. And you might be like, well, that wasn't terrible math. I mean, I can do that math. That's not a big deal. I'll just do the math. Okay, cool. Be my guest. Do the math on this one. I didn't think you wanted to either. So you could FOIL all this out if you wanted to. That's what you would have to do if you wanted to figure it out, but do you want to do that? I don't. So let's not. Let's instead, in order to find the degree and leading coefficient, if that's all that we care about, all we need to do is just multiply all these terms together. Sine and all. All of these terms. Let's do it. 2x times 3x times negative 2, that's a terrible times negative 2x times x times 1/3 x. That is, let's get all the numbers together. That's a 1x. That's 2 times 3 times negative 2 times 1 times 1/3. Times, and then there's, look, 1, 2, 3, 4, there's 5 x's. So there's 5 x's, that's x to the 5th. So we know the degree. 2 times 3 is 6, times negative 2 is 12, times 1 is still negative 12. Negative 12 over 3 is negative 4. This is negative 4x to the 5th. That's the leading term, which makes our degree 5 and our leading coefficient negative 4. That is so much easier than doing all of that FOILing. You don't want to do all that FOILing. That would take all day, and ain't nobody got time for that. So that's a quick and easy way to tell the degree and leading coefficient of this particular function. Now, let's think about why we care about any of this. And it's because of end behavior of polynomials. So in this example, I want to determine the end behavior of this polynomial. Okay, so we've done end behavior for functions, and we've done a bunch of stuff with degree, so maybe I can bring those together and marry them. So figure out what the degreed term is. That is the leading term. Is this term right here? Okay, treat that term like everything else doesn't exist. Just forget that any of this exists. And to find the end behavior, this is a positive, odd function. Positive, odd functions at their ends look like this. So as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. That's it. That's all that we do. But why? Why is that true? Well, let's rewind for a second and think about this. Okay? So we know that that's true. That is what you're going to get. Because, think about this. What we're thinking about is as x goes to really big numbers, either really big positive numbers or really big negative numbers. Think about plugging in bigger and bigger and bigger numbers, like 1,000,000, 1,000,000,000, 1,000,000,000,000, a quadrillion, ginormous numbers. 1 billion to the 5th power is so much bigger than 1 billion squared is just so much bigger than 1 that this leading term is going to dominate the other two. It's going to be so much bigger. And since end behavior is only concerned with us getting really big numbers, even bigger than a billion, the only term that we care about is this first one. We don't care about the other two, so we only need to consider the first one. That is, we only need to consider the power function inside of the polynomial that has the degree in it. It's not necessarily always the first in the order. Let's look at these couple of examples. Determine the end behavior of f of x is negative x to the third plus 3x to the sixth plus 1. So we're going to go off negative x to the third, right? It's the first term. We should go off the first term, right? No. Find the one with the degree. That's 6. And here's the sign. So it's, you can write this, it is positive and even. Positive even functions look like this. Go look at your table that I hope you copied down. And if you didn't, go back in the video and copy it down. As x goes to negative infinity, or as x goes to positive infinity, y is going off to infinity either way. That's the end behavior. It depends on the degreed term. That is the term that has the degree in it. That's the only term you care about. As x gets super big or super small. Let's look at this one. Obviously, this is the term we care about. So this is negative odd. Negative odd, go look at your table, looks like this. So as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to negative infinity. That's all that there is to it. Find the term with the degree in it, and then use your table, or just have it memorized, and you know the end behavior of it. All right, let's talk about one more little thing real quick, and then we're done. About the x and y intercepts. So the intercepts of any function, including those of polynomials, are found as such. To determine your x-intercepts, you just set the function equal to 0, and you solve it. To determine the y-intercepts, you just set x equal to 0 and evaluate that expression. This next example asks us to do just that, for f of x is x times x plus 1 times x minus 4. So to find the x-intercepts, like it says up here, you just set f of x equal to 0. When we do that, we get x times x plus 1 times x minus 4 equals 0. That is f of x, this f of x right here. It's just this. So I just copy and paste it, and I set it equal to 0. So here's where I did that. You can see that I did that. And so we end up using something called the zero factor property, which says that if we're going to, and I'll use a different color to underline this, if we're going to multiply x times x minus 1 times x plus 1 times x minus 4 together and get 0, then 1, 2, or all three of those products have to be 0. The only way for you to multiply a long string of things together and get 0 out is if one or more of them is 0, which means you've got three different things. You've got x equals 0, x plus 1 equals 0, or x minus 4 equals 0. And you've seen and used this multiple times before. It's called the zero factor property. And so all that I did was come in here and I solved each one of these. So solve x plus 1 equals 0, you get x equals negative 1. Solve x minus 4 equals 0, you get x equals 4. And you might think that you're done when you've copied everything in this left-hand box. When you've done all that work, you might be like, oh, those are the x-intercepts. That's what we were asked to find, the x-intercepts. No, bad. Those are not the x-intercepts. The x-intercepts are the things in this right box here. That is, the x-intercepts are the points, whatever you got, comma 0. Whatever you got, comma 0. Whatever you got, comma 0. That's what we're looking for. Those are x-intercepts. X-intercepts are points. This thing in this box here on the left, these are just your zeros. These things over here, these are your x-intercepts. There's a difference. Your y-intercept, we're just going to find f of 0. That's it. To find f of 0, you just plug in 0. So I plugged in 0 for x there, there, and there, did some simplification, and we got 0 out. So it's 0, comma, whatever you got. That's the y-intercept. This is not the y-intercept. This is not the y-intercept. Okay? This point, this coordinate, is the y-intercept. And that's how you find the x and y. For anything, and I'm going to say it again because it's worth saying it again, to get the x-intercept of literally any function, including polynomials, to get the x-intercept, you set it equal to 0 and solve. To determine the y-intercept, you plug in 0. To get the x-intercept, you set the function equal to 0 and solve. To get the y-intercept, you set x equal to 0 and evaluate. That is, you plug in x equals 0 to get the y-intercept. You set the thing equal to 0, the function equal to 0, to get the x-intercept. I'm going to say that one more time, and if you haven't actually written this down on a piece of paper, you should do it, because we do it a lot. We do it in trig, we do it in calculus, you do it all the way through mathematics. To determine the x-intercepts, or the zeros, you set the function equal to 0 and solve, because you're wanting to figure out what it is when y is 0. So if you get 0 out, that's equaling 0. So you set it equal to 0 and solve. To determine the y-intercept, that's what happens when x is 0. That's how you're on the y-axis. So you plug in 0 and you evaluate it. That's all that there is to that for literally any function. Doesn't matter what the function is. You want to find the x-intercepts, you set it equal to 0 and solve. You want to find the y-intercept, you set it equal to 0 and evaluate. Let's look at these last few examples. I want to find the x and y intercepts for f of x is x squared plus 8x plus 12. And you'll notice that all the math's done here. I'm just going to walk you through it. So what I did was to find the y-intercept. Let's go over here and look at the y-intercept first. I just plugged in 0. Found f of 0. I plugged in 0. So remember, it looks like 0 squared plus 8 times 0 plus 12. That's up here. Because f of x looks like x squared plus 8x plus 12. Cool. So plug that in, you get out 12. So your y-intercept isn't 12, it's 0, 12. That's super easy, barely an inconvenience. However, to solve, to find your x-intercepts, you're just going to set this thing equal to 0 and solve. So let's do that. So here I did that. I set it equal to 0 and solve, and I factored it. You've factored things before, I know you have. The game works like this. What two numbers can you multiply together to get 12 that you can add together to get 8? 6 and 2. 6 and 2. 6 times 2 is 12. 6 plus 2 is 8. So this factors as x plus 6 times x plus 2 equals 0. And then you just use the zero factor property. If these two things are going to multiply together to give you 0, then either x plus 6 is 0 or x plus 2 is 0. And then solving each of those gives you this. Either x equals negative 6 or x equals negative 2. Now, if I asked you to find the zeros, you would be done when you got to this box. But you're not done when you got to this box, because I asked you to find the x-intercepts. So please write it like this, or it's wrong. I appreciate you. If you're wondering why I'm going so fast through this, it's because this should be review up to this point. But if you want me to go over it again, the great thing about a video is just rewind the video and watch it again. Take some notes, pause. If you haven't paused the entire time and actually written down anything I've written, you may not be doing it right. Now, maybe you're capable of learning this by just watching the video, full speed, taking no notes, and you just get it in your brain via osmosis and you know what you're doing. That's okay. But most people should probably be pausing the video and actually, writing stuff down, because you learn by writing in math. That's just how it works. So let's talk about this last example of intercepts. I've just scrolled down a little bit here. It says, find the x and y intercepts for f of x equals x to the fourth plus 8x squared plus 12. And this is a quick little sort of preview. We're going to go over this more in depth in a future section. But for now, the y-intercept is found by plugging in 0. So if you plug in 0, you get out 12, and your y-intercept is 0, 12. That was no big deal. I knew it was going to be this before I even started. To find your x and y intercepts, though, I want you to look at this. I want you to look at this very carefully. So let's look at this. If you write down the actual thing itself, you'll notice that we have 8x to the fourth, we have x to the fourth rather, plus 8x squared plus 12 equals 0, right? Look at the pattern here. This goes 4, 2, 0. Because it does that, we can still factor. Except the factors aren't going to be x's, they're going to be x squareds. If there were an x cubed or an x to the first term anywhere in this entire thing, we wouldn't be able to do this. But since it steps down by 2, we can put a 2 here. If this stepped down by 3, if this went like 6, 3, 0, then we could put a 3 here instead, if we wanted to. And then we play the rest of the game We play the rest of the game pretty simply by just the same way we've always done it. What two numbers can I multiply together to get 12 that I add together to get 6? That's how you get 6 and 12. And then you get the zero factor property gives you this part or this part, and then you just solve each part. That's pretty easy to solve. Notice that when you go from this step to this step, you get a plus or minus. Don't forget that. That's how you get all of your roots in here. And if you forget that, you're not going to get all the roots. But the important thing is you get these two answers. You get x equals plus or minus root 6i. That's two answers. And then you get plus or minus root 2i. That's two more answers for a total of 4 answers. The question was find the x-intercepts. So what are the x-intercepts? You found the roots, or the zeros. You found them. Congratulations. There's 4 of them. They have little yellow arrows pointing to them. They're these guys. However, what are the x-intercepts? The x-intercepts are points at which the parabola itself actually crosses. These are imaginary numbers. So don't let me get you with this, guys. The x-intercepts? There are none. If you get out only complex numbers, then there are no x-intercepts. Now, if you get out a mixture of complex numbers and real numbers, your x-intercepts are the real numbers, comma 0. Like we talked about before. But in this case, there are no x-intercepts. Because these points down here, that's 2 of them and that's 2 of them, those aren't even real numbers. The x-axis itself, that's real. So it actually has to be on that axis in order for that to work. So don't let me trip you up with that. Now I want to talk about one last little thing, and we're done here. Let's talk about the fundamental theorem of algebra, and we're going to talk about it more in the future, so I just want to really quickly go over this. It says, for n some natural number, and each of your a sub k's done like they're supposed to, a polynomial function that looks like a polynomial has, and here's the key, at most n real zeros, roots, or x-intercept. Okay? It has exactly n complex roots, zeros, or x-intercepts. Okay? It has exactly n complex ones, which we'll talk about in the future. But for now, we're going to say it has at most n real zeros. So, here's the 2 quick little problems. We say, how many x-intercepts does f of x equals x to the 4th plus 8x squared plus 12 have? Well, 4. That's the largest power, so it has at most 4 is what we say. How many x-intercepts does 6x cubed minus 4x to the 20th plus 11 have? 20 is the degree, so it has at most 20 x-intercepts. Maybe less. Maybe it has none. Maybe that has none. I don't know, I've never graphed it. But it has at most 20 x-intercepts. That's what we can guarantee. And we can also guarantee that this polynomial up here in example 22 has exactly 4 complex roots, and that this one in 23 here has exactly 20 complex roots. And remember, real numbers can be complex numbers, so when I say it has exactly 20 complex roots, I don't mean that they all look like 6 plus 5i or something. It might be just 6, because remember, 6 is just 6 plus 0i. That's the fundamental theorem of algebra, and it's not super important that you get it right at this exact moment, but we will be going over it in the future, and I wanted to go over it so that I could just, so that we could just go back up here for just a moment and look at this. I said find the x and y intercepts for this guy, and if you pause the video and worked through this beforehand and found this, that's awesome. Look, I found 2 here and 2 here. There's 4 total. I said there'd be 4 total, says the fundamental theorem of algebra. So how's that useful? Well, I know that I got them all. Because previously, we didn't know that we got them all. Now I know that we actually found all of them. Because it would be truly awful if this thing had 5 answers and you only gave me 4 and didn't know how many you were supposed to be finding. So that's useful. Find the degree, and it will have, at most, that many real answers, but it will have exactly that many complex answers. And since we're working with complex numbers now, you better have as many answers as there are degree, or you didn't find everything and you're not yet done. But overall, that's everything that I wanted to go over, and I'll see you in the next one.